Hello everyone, I welcome you to today's lecture. What we discussed last time about IBX based oxidation, isoxybenzoic acid based oxidations. I hope that you had the chance to go through that and understand what I mentioned in the class, where not only we did the oxidation of alcohols to the corresponding carbonyl compounds, but we also discussed how alcohols can be converted to the corresponding enone or dienone, and how the mechanisms allow the conversion of ketones to the enone using IBX in a involving radical based mechanisms. Now, one of the oxidizing agents that we used for converting an enone or transposing an enone to the corresponding enone with an extra functional group such as this was Dauben rearrangement, where we took the alcohol and reacted with PCC. Now, that oxidizing agent pyridinium chlorochromate allowed this oxidation of the tertiary alcohol, which can be formed from here if we add the corresponding alkyl or aryl group, and then we carry out this Dauben rearrangement. So, if one also looks at the IBX based reactions, so in 2004 someone reported the similar type of conversions using IBX in DMSO at 55 degrees temperature. So, as one can see that we can have not only PCC but also IBX as a reagent to bring about this Dauben-Michno rearrangement. Now, as you can anticipate that the intermediate that can be expected to form on this intermediate would be something of this kind. So, if one starts with this substrate which is shown above and reacts with IBX, that is what you have is something of this kind, where you can put the iodo here and oxygen here, and of course OH and OH, and iodo iodine oxygen double bond and OH from the IBX, and what one can expect to form is an intermediate of this kind, where you have the reagent in this fashion and with an O minus and positive charge. So, when this alcohol reacts with this iodine, this goes off, and what you generate is something of this type by the loss of water from the reaction medium. Now, when such a intermediate which is formed, you can anticipate that the iodine here, which is the iodine here which is connected to the O minus, which of course we can write as I double bond O or I plus and O minus, then we can anticipate that this is 1, this is 1, this is 2, this is 3, this is 4, and this is 5, and this is 6. So, you can anticipate that this oxygen can be attached to this with the double bond movement of this kind and of course here something of that type can occur to form the intermediate of this kind, where now you have a hydrogen and you have an R and then you have an O, then you have an I, then of course you have the bulk of the substrate here, and oxygen here and this here, and at the same time what you will have is an O minus coming here, which is what is like this. Now this can undergo oxidation, this allows oxidation to take place, and one can get the enone here transposed and plus IBA. So it is very similar to what we discussed earlier with pyridinium chlorochromate, but now you have another option of using IBX for the similar type of Dauben-Michno rearrangement to take place. Now we look at other oxidizing agent, which is called as a Prevost reaction and its modification. Now Prevost reaction gives either trans or the anti or syn alcohols, depending on the condition that one uses, or trans or cis alcohols Now what is used is the olefin is allowed to react with silver salts of a benzoic acid or acetic acid, that means silver benzoate or silver acetate, and in the presence of iodine in a reaction where benzene is used as a solvent, and what is formed is the dibenzoate, which is formed from the olefin, which can be hydrolyzed under basic conditions to form the diol. As one can see from here that the benzoate, which is here, is coming opposite to the other benzoate which is present. That is the reason why this hydroxy group and these hydroxy groups are opposite to each other onto the double bond side. So what is exactly happening is silver benzoate interacts with the iodine and polarizes the iodine to form silver iodide, and you generate an I plus. This I plus then interacts with the double bond to form an intermediate iodonium ion of this type, and of course here in this case you will be losing silver iodide. Now benzoate can attack say on this carbon atom here, and this bond breaks, the carbon iodine bond breaks, and you now have benzoate attack. So this there is an inversion of stereochemistry at this center. So the R2 group and R3 groups are pointing upwards, and from the lower side benzoate is attacking, and now you have iodine going on the top, where now the next silver benzoate, there should be positive charge here on the silver. Now this interacts with the iodine, tries to pull it off. At the same time this oxygen lone pair of electrons can attack here, and by pushing the iodine out, which is assisted by the silver salt, to form an oxonium ion intermediate of this kind. This of course we can write as a resonance structure with a positive charge either on oxygen or on carbon. Of course you will prefer to write the positive charge on the carbon, which is next to the phenyl group, and in this case now this symmetrical intermediate then is attacked by the benzoate onto this carbon. Now when this attacks on this carbon, now this particular benzoate has come from the opposite side of the other benzoate, because now this particular part becomes a benzoate. This particular part becomes a benzoate. So now you have a dibenzoate where the two benzoate groups have come from opposite direction, and when the hydrolysis and the basic condition is carried out, the benzoates get oxidized and you get a corresponding diol. So this is where one of the aspects of Prevost reaction, which was discovered long back, has been used. One of the disadvantages, as you can see, is the use of silver salt, which is somewhat expensive if the reaction is to be carried out on large scale. But it is very interesting from the mechanism point of view, and now there is some modification which is done, and that has been reported by the famous organic chemist R.B. Woodward at Harvard, who found out that if the reaction is carried out in the presence of water, in this case of course the reagent that has been taken is silver acetate, but it does not matter, one can also take silver benzoate. Idea here is that you have a source of any carboxylate which eventually gives the hydroxy group. So when the reaction is carried out in the presence of water, what is observed is the formation of the cis hydroxy groups. That means the two hydroxy groups are coming from the same side. Now if one looks at the mechanism that we discussed, without the presence of water you get an intermediate of this kind. Now this intermediate is the one in which we had attacked the benzoate. In this case of course it would be acetate, but in the case of benzoate, the benzoate attacks onto this carbon here, in this carbon here, and this opens up here from here to here, and you get the corresponding trans diacetate or dibenzoate. So what we had observed last time was the like this here, and of course OCO phenyl, and you get an OCO phenyl. So basically we were saying that this part and this part are opposite to each other. So that is the case when the benzoate or in this case acetate. You can also have an acetate reacting. So that attacks opposite to on the opposite side. But if we take water as a medium, I mean as a nucleophile present in the medium, then the water now is competing with the acetate or the benzoate moiety, and the water is small, is present in a large amount, and it attacks onto this particular carbon atom rather than attacking onto this carbon atom, and that is to do with hard soft acid base principle. That is, this carbon is a positively charged carbon with two oxygens around, and water is harder than the benzoate or acetate where the negative charge is delocalized over the carbonyl group, whereas in the water case it is not delocalized. Therefore this is a hard base and this is a hard acid, therefore the reaction preferentially gives this particular OH group attaching onto the carbonyl where there is a phenyl ring. Now this obviously will immediately break up and releasing the OH and the benzoate, which of course on the hydrolysis will give the OH. Now in the two OH groups are on the same side. Obviously here we are writing benzoate because we are comparing with the previous reaction that we did it, but we can also have the acetate as I mentioned here. So in place of this benzoate part, here you can have the acetate part also. So one gets the diol which is cis diol. So this is a very interesting modification that has been introduced by R.B. Woodward. Now if one looks at a complicated example such as this, which is an intermediate for a steroid type of synthesis. Now if one takes silver acetate and iodine, so obviously since the methyl group is beta oriented, the sterically less hindered side will be from the alpha side. Therefore iodonium ion formation takes place from the alpha side. Now if one then attacks the acetate, now this reaction we are carrying out in the presence of water. So it is, since the iodonium ion is formed from the alpha side, the attack of the acetate ion would always occur from the beta side and on the less hindered side of the iodonium ion, but it does not really matter eventually because we get anyway the diol. So but the reaction occurs from the beta side, that is the reason why what we are getting is an intermediate where this diol would eventually come from the beta side, because the intermediate that is going to form will be something like this, and here you have O, C, O and methyl. So now if this reaction goes further, then we will get O which is beta, C, then this here O and this. So this is also beta and this is also beta, and then of course you will have methyl group here and the positive charge here. This is what is going to happen. And when this is attacked by the water, then of course what we would get is an intermediate of this type where you have an OH here and the methyl here. When this part breaks up in whichever way, eventually finally what one would get is OH here and of course OH here. So this is how the reaction is carried out. Now that means if the iodine reacts with silver acetate and the iodonium ion is formed from the alpha side, the diol is beta. Now if one carries out the dihydroxylation using osmium tetroxide, then similar to the iodonium ion formation, osmium tetroxide would also attack from the alpha side because there is a steric hindrance from the beta methyl group. So the osmium tetroxide would make an intermediate of this kind which is from the alpha side, and since it is a cyclic intermediate involving both the oxygens of the osmium tetroxide attacking on the double bond from alpha side, eventually one would get the diol in which both of these hydroxy groups are alpha oriented. So one can see that the difference between the two of them is eventually the outcome of the diol's stereochemistry. So this kind of application has been very well utilized in the reaction of Prevost type. Now there are disadvantages, as I mentioned, that you use 2 moles of silver salt and 1 mole of iodine. It is something which is not very good, because if one carries out the reaction on a large scale, then you have this as expensive protocol. So these protocols involving silver salt and iodine are expensive. So what has been recently reported in 2005 is you take lithium bromide as a in a catalytic amount as a source of Br minus and lithium plus, and this can be reacted with 1 mole equivalent of an oxidizing agent, which is phenyl iododiacetate. Now this phenyl iododiacetate oxidizes the Br minus to Br plus, and then of course that Br plus and the Br minus will eventually become a bromine. So now this molecular bromine, in the process of course you get iodobenzene and lithium acetate from the oxidizing agent, which is phenyl iododiacetate. So basically what you have done is you have oxidized the Br minus, the bromide ion, to the corresponding molecular bromine, which then reacts with the olefin in a similar fashion as the iodine was reacted with the double bond in the Prevost reaction, where silver salts of the benzoate or silver benzoic acid or acetic acid was used as silver salt. So when this bromonium ion is formed, we will get of course the attack of the double bond onto the Br plus taking place exactly in an identical fashion as iodine type of reaction, and then when the attack of the acetic acid or in this case acetate or acetic acid occurs, then one can imagine that the nucleophile coming from the beta side and this particular bond breaking from the lower side, and therefore the acetate and the bromine, the acetate and the bromine would be opposite to each other. It is very clear that this is what exactly will happen, similar to the Prevost type of reaction. Now obviously you have the acetate, which is now going to react it from the opposite side in the presence of this bromine leaving group in the form of bromide, and you generate a similar intermediate to the Prevost type of intermediate. Now it is very clear that the acetic acid or acetate ion would now attack from the opposite side, and then you get an antidiol or antidiacetate, which can be hydrolyzed to the corresponding antidiol. But if water is added like Woodward's modification, then this is the intermediate that can be attacked by the water, and then you have a similar situation as Woodward's case, and you can get the cis-diol or syn-diol that will form when water is added. So it is exactly similar to the Prevost reaction. The only difference is that in place of iodine as a molecular iodine and silver salt of the benzoate, what one is using is basically nothing but lithium bromide in a catalytic fashion. Now as you can see from here, when the reaction takes place, you have a bromide ion coming from here, there is also bromide ion coming from here. So you have two of the bromide ions which have come out of the reaction medium, and acetic acid or acetate, they react, and then of course you generate the intermediates which are diacetates or either in anti-form or a syn form. But this bromide ions then are reoxidized by the same oxidizing agent, which is phenyl HIOAC twice, and you regenerate the bromine here. So you do not have to use molecular bromine, and you can take the corresponding lithium bromide and then carry out by reacting with phenyl iododiacetate as an oxidizing agent to form the corresponding syn or anti-diacetate. So this is a very interesting modification and new modification and relatively cheap modification. Now we have another reagent which is called as Fetizon's reagent, which exploits the utility of silver carbonate which is essentially adsorbed on the surface of sealite, and although this allows the oxidation of primary, secondary alcohols both, but it is more selective for the oxidation of secondary and allylic oxidations, or in other words the secondary and allylic alcohols are preferentially oxidized over primary if the substrate has such both the kind of alcohols which are present. Now Fetizon oxidation involves oxidation of primary and secondary alcohols utilizing the compound silver carbonate, which is adsorbed on the surface of sealite. Basically sealite is nothing but diatomaceous earth, also known as kieselguhr, is a naturally occurring soft siliceous sedimentary rock. So basically it is a fine powder, white color powder, which has mainly SiO2 as the chemical present. However, it allows adsorption of different kinds of chemicals on its surface. It is known as Fetizon's reagent because it was first employed by Fetizon in 1968. It is a mild reagent suitable for both acid sensitive and base sensitive compounds, and it is specifically reactive with lactols to obtain lactones. Now this is something that we will discuss from diols, not from diols, from diols. Obviously it is an expensive reagent because it is a silver salt which has to be utilized. However, it has lot of advantages. One, as I have mentioned above, it has a selectivity in terms of secondary and allylic alcohols are oxidized faster than primary. The diols can be interestingly oxidized to the corresponding lactones. The only disadvantage, or one of the disadvantages of this reaction, is that it can be utilized, but if there are polar groups present on the substrate, then there is a problem, because those polar groups can have a competition with the silver carbonate for the alcohol adsorption, because ultimately silver carbonate, which is adsorbed on the surface of sealite, interacts with the hydroxy group of the alcohol. But if there are other polar groups which are present in the reaction medium or on the substrate, then there is a competition. Now there is also a possibility of steric hindrance of the alpha hydrogen. That means the alcohol which is getting oxidized, that alcohol, if it has the hydrogen which is sterically hindered kind of oxygen hydrogen, then there is a possibility of a rate slowing down because of the steric hindrance that is exhibited by that particular substrate. So in case the reaction is carried out in a solvent which is polar, then also there is a problem. Now I just want to show one or two examples here. For example, if this allylic alcohol can be oxidized to the corresponding enone, this allylic alcohol can be converted to the corresponding alpha beta unsaturated aldehyde, and as I mentioned that you can take a diol of this type, and it is a symmetrical diol, so you get only one particular lactone, and then if you have this diol which is not a symmetrical diol, but then as you can see the difference, there is an allylic alcohol here and this is a non-allylic alcohol here. So this particular the OH group gets oxidized to the corresponding aldehyde, which is in equilibrium with this lactol, and this lactol then is again allylic alcohol and it gets oxidized to the corresponding lactone. So, this is how the lactone has formed. So, one can go to the diol to the lactone in two different ways as it is seen. One diol which is a symmetrical diol which does not have allylic alcohol, but then this is allylic alcohol. So, allylic alcohol is oxidized faster than the non-allylic alcohol, and that allows the lactone formation in a very regioselective fashion. So, these are the examples which indicate the utility of silver carbonate on silicate, which is called Fetizon's reagent. So, I will stop it today at this stage and take up the further aspects of this Fetizon's reagent in my next class. In the meanwhile, you can go through these oxidations which I discussed just now, both the Prevost reaction as well as the silver carbonate based reaction, and prior to that I discussed the IBX based Daubner Dauben-Michno reaction or rearrangement, and you can carefully look at the mechanistic aspects and application of those reagents in organic synthesis, and then we will look at further aspects of these in the next class. Thank you.